and these are vectors. Okay, O2P is O2P. Fine. Now this can be written O2P in global frame. This vector can be written using its components along the x2, y2, z2 directions. Okay. So what we have here is the component of O2P in the x direction, in the y direction, and the z direction. And these are the unit vectors in the x2, y2, and z2 directions expressed in the global frame. That is why it is after the curly bracket the subscript 1 is there. So again, this particular vector, the scalar into a unit vector, is actually the component of this vector in the x2 direction, and this is the component in the y2 direction, and this is the component in the z2 direction, all expressed in the global frame. So now this quantity okay, can be written in a short form. You consider a matrix. This is a linear operation, so you can use matrix algebra for representing that. So you have a matrix whose column vectors are precisely these unit vectors along the coordinate directions, expressed in, of course, the global first coordinate frame, and this then becomes a 3 by 3 square matrix. Okay, that multiplies this column vector. And what is a column vector? Column vector are these components, these scalars, and these scalars are nothing but the projections of these along these directions, and so that is nothing but the location of this in the local frame, this frame 2. And so O2P, so this square matrix pre-multiplies this column vector O2P, which are made up of components of P in the frame fixed to the rigid body. So what we have done is, this thing we have written in a shorthand form like this, which further this particular matrix is called a rotation matrix from 2 to 1, which transforms a vector in 2 to a vector in 1. Okay? It is a 3 by 3 matrix, and that it is post multiplied by the local coordinates of the point, and this is the vector from the global frame to the local frame origin. Okay, so this particular equation, which is a very important equation, transforms, given the position of a point in the local frame, which is specifying where the point is in the local frame, and given these two entities, we get the location of P in the global frame. Okay. So this is a very important equation, and it is a very important relation. This, now take a look at these two things. Imagine that you are changing this continuously. Okay, so this doesn't change. What is this? The column vectors of these are the unit vectors in the directions of the axis fixed, we have fixed in the body. So when we change this not changing really means that the directions of these three vectors fixed to the body are not changing. What it means is that the body is not rotating, it is only translating. So when we change only this, the body purely translates. So O1, O2 represents translations of the body, and if we fix this and change this, because this cannot be arbitrarily changed, it has to be changed with some conditions, whereas this can be arbitrarily changed because the three components of that vector are independent of each other, whereas the 9 components of this are not independent of each other. But suppose we change it with certain constraints, then what happens is that this point remains where it is, and the body is rotated. Okay, so this corresponds to, parameter corresponds to translation, this corresponds to rotation, and by position and orientation of the rigid body, for specifying that, I will simply give values for this vector and values for this matrix. So that represents those two entities. Sorry. Those two entities represent position and orientation of the rigid body. Okay. What was the claim? The claim was that claim was that once you give values for them, once you are given a point on the rigid body, any point, okay, by giving the value of this, then I can find out its position in the global frame once this and this are known. And what about directions of line? I'll come to that and show you that this is all that you need for getting that too. Okay? But let us look at the properties of these a little more, the rotation metrics particularly. So, again, this is the equation which transforms a point's position in the local frame to its position in the global frame. It requires this vector, column vector, and this 3 by 3 matrix. Okay. Now look at this 3 by 3 matrix. We have already seen that these column vectors, columns are these vectors, unit vectors in these directions in the global frame. And because that is so, okay, typically the way we choose these vectors, they are mutually orthogonal. So what it means is that these columns are mutually orthogonal. Okay. Not only that, they are unit vectors. We represent the direction by unit vectors. So they are unit vectors. Because of that, this is called an orthonormal matrix, and this is called the rotation matrix. Okay. So I am just talking about some of its properties. Because it is orthonormal, it turns out that if you pre-multiply it with its transpose, then you get the identity matrix, which then means immediately that the inverse of the rotation matrix from 2 to 1 is nothing but the transpose of the same matrix. Okay, that's a very big advantage, because in order to do inverse, typically you have to do a lot of calculation of the order of 3 kind of complexity, but whereas in this case you just do a transpose. Okay, that follows from the fact that this is orthonormal. It can be very easily seen. And by the way, the rotation matrix, inverse of the rotation matrix from 2 to 1 is nothing but the rotation matrix from 1 to 2. Okay, so that is what. Now comes the important thing. If you have a free vector, so take any direction vector here, we express in 2, so let's say fixed to this. So some vector that we have marked on this body, its direction in the global coordinates is obtained by just pre-multiplying with this rotation matrix. Okay, this can be easily seen, because if you take a point P here and another point Q here, a vector from Q to P is nothing but the position vector of P minus the position vector of Q. In that subtraction, this quantity disappears, okay, and you end up with just the rotation matrix. So this is what happens. So any direction given by free vectors, transformation is obtained by just multiplying by rotation vectors. So my claim that given these two, I can get the position of any point on the rigid body and the direction of any line on the rigid body now is justified because of this relation and this relation. Okay. So now we can use these two entities to stand for, to represent position and orientation, or rather pose of a rigid body. Now you can also see that this free vector multiplication follows the chain rule. From the free vector multiplication we can show that the chain rule holds. That is, if you want to get the rotation matrix from 3 to 1, it can be done through another frame, the second frame. So the rotation matrix between 2 and 1 was multiplied by rotation matrix between 3 and 2. So this also follows. Okay, and because of this, actually many of the calculations algebraically look very simple. Of course, if you get into the details, it could become complex. Now, before applying this to our case, let me look at some alternative ways of representing. One is orientation. Okay, the person who originally thought a lot about orientation and came out with many representations was Euler, and Euler came out with what are called Euler angles for representing orientation itself, or orientation alone. And rotation matrix has 9 elements, out of which only 3 are independent. You can show this. It comes immediately from the fact that in this rotation matrix, there are unit vectors as columns. So immediately there are 3 relations which relate the elements. In addition to that, if you take a pair of columns, they are orthogonal. So there are 3 more relations. So there are 9 variables which are related by 6 relations. So there are only 3 independent quantities. Okay? And Euler came out with a way of doing that using 3 independent angles. And this is, there are many ways of doing this. I am not going to discuss it in detail, but you can look up a typical book for this. But this is an alternative way of representing the orientation or rotation. Now, we use this particular relation to transform the position of a point on the body in its frame to its position in the global frame. Okay? That this particular relation is inhomogeneous because this extra term is there which is not multiplying this. So we can actually transform things a little bit to make it a homogeneous transformation. So what we could do is we can write the same thing exactly the same way. Okay, where an extra term doesn't appear. Only we cannot use the same vector for position. It has to be slightly transformed. And this transformation matrix is no more 3 by 3, it is 4 by 4. So a vector is written as its x, y, z components and augmented by the number 1. It's a 4-dimensional vector. Okay? It's a column vector still. So these have to be augmented and made 4-dimensional vectors. And the transformation matrix, this is called the transformation matrix now, from 2 to 1, has the following elements. Its top left 3 by 3 submatrix is the rotation matrix. You have 3 zeros here and a 1 at the bottom right corner. And this, on the right hand side column vector, the first 3 elements are nothing but this. Okay? So if you construct a matrix like this, then this operation is correct. And because of that, now this is a simpler form than this, immediately you can apply chain rule to that. So the transformation matrix now can stand for position and orientation of the rigid body. Earlier we were using this position of the origin and the rotation matrix. They are combined into one in the transformation matrix and the chain rule follows. Okay? So it makes the algebra very simple. You can see the advantage of that a little later.